the current flow through it. Those are directly proportional, and the proportionality constant is called resistance. Capacitance and resistance can both be determined by the physical construction. And then we can also talk about what function these devices play in a circuit. The function of a capacitor is to store energy, and the function of a resistor is to dissipate it. So we were talking about the quote-unquote standard charging circuit. That's what I've drawn here. If you're wondering why I call them the standard charging and discharging, it's because we will take a look at the possibility of a non-standard circuit a little bit later. But basically what this circuit consists of is it's a battery charging a capacitor, and that's happening through a resistor. So what we talked about is that generally speaking, since the resistor and capacitor are in series, this does subdivide into three distinct equipotential regions, which I've labeled A, B, and C, lowercase c, which is an equipotential, not to be confused with uppercase C, which is the capacitor. And we talked about the progression of what happens here. While the voltage across the resistor and the voltage across the capacitor do have to add up to the battery voltage, which is fixed because they're in series, this voltage waterfall has a time evolution because when the capacitor is empty, it has no voltage drop yet. So when Q is 0, the voltage drop is 0. But then as it fills, it takes more and more of the voltage drop, and of course, since there's only so much to go around, it basically displaces the resistor out. So VC increases while VR decreases. So if this is the generally what it looks like during the charging process, the ratio of how much is in one versus how much is in the other will change with time. In fact, at the very beginning, before the capacitor has any voltage drop at all, regions B and C are 1. Okay? There's no voltage drop from B to C. So region B actually starts out here aligned with C. All of the voltage drop actually happens across the resistor at the beginning. So the entire voltage drop is across the resistor. The capacitor doesn't have any yet. So we see that. All of the voltage across the resistor, none across the capacitor. Again, why is there no voltage drop across the capacitor? Because there's no charge on it yet. And if it's not across the capacitor, it's got to be across the resistor. And so, of course, if there's voltage drop across the resistor, current will flow. That's what charges do. They'll flow across the resistor because there's a voltage drop available. Now, as charge builds up on the capacitor, and that voltage drop increases, B is starting to now creep up, and the top of the line here is when B aligns with A. That's when the capacitor's built up so much charge that the voltage drop across it here is the same as the voltage drop across the battery. So now B has joined up with A. Well, if A and B are the same voltage, there's no more charge that would flow, because why would charge flow from A? Because it's the same voltage as B. So now, because there's no voltage drop across the resistor anymore, the current shuts off. So now that there's no reason for charges to flow across the resistor, the current shuts off, which means we don't get any more onto the capacitor. So at that point, we're at whatever our full charge is. Okay? So the charging process is complete. The charging process is complete when the capacitor voltage has grown to be that of the battery which charges it. That is the end of the line for how much charge you can get on there with this battery. So notice the trend here is that everything having to do with the resistor decreases to 0. Everything having to do with the capacitor increases now. So that's a marked contrast from the standard discharging circuit, which we did and completed last time, where everything runs down to 0. Now you have that everything having to do with the resistor runs down to 0, but everything having to do with the capacitor grows. Okay? So if you go onto the equation sheet, the exam equation sheet, we'll find these three formulas. These are the bare minimum of what you need. This is current function is for both charging and discharging. That's your standard decaying exponential. It runs down to 0. It looks like this, just as a reminder. because whether you're charging or discharging, eventually you run out of something to do. The current stops flowing because either you're done filling or you're done emptying the thing. But there are two charging equations. One's for filling and one's for emptying. This one is the discharge equation. If you just look at it, you know that it runs down to 0. But the one we have to look at here is the charging equation. This is the charge equation. That does have an exponential, but that extra fancy feature, the 1 minus, is actually what makes sure that it grows. So this is one of the functions that we just ran out of time. I didn't have a chance to look at this, so let's do it now. Let's evaluate that function at several different times. So first of all, we can plug in t equals 0. E to the 0, or anything to the 0, is 1. But now it's 1 minus that, so we find that at the beginning, our capacitor is empty. That's what we're expecting. This is the charging circuit. We're starting from nothing. We can go, of course, plug in a very long time. 1 minus e to the negative infinity. This is going to be, as I talked about last time, 0. Whoops. But 1 minus 0, this gives us Q full. So after we wait a very long time, we will have achieved the full amount of charge. Okay? So this indeed does grow. This is not decaying with time. This is actually increasing from nothing to full. We can graph what this looks like. It looks like this. If we mark off Q full as this asymptote that we don't ever approach until we wait till forever, it goes something like this. So it does have that curved shape that comes from the exponential. And that's to recognize the fact that at first, when the capacitor is empty, it's easy to fill it very rapidly. But it becomes more and more challenging, of course, to do that later on. You've got a lot, if you've already had a lot of charge accumulated on this, it's harder to get that much extra drop more. Remember, toward the end, B is almost the same voltage as A, so the amount of current that would flow from A to B is minimal. So it becomes harder and harder. In fact, you have to wait forever for it to charge perfectly. Okay? So if that's going to be the answer for every circuit, then obviously we need a better benchmark, and we again use this thing called tau. So let's check out what happens at t equals tau. So we get this. E to the minus 1, we said that was about a third. 1 over e, it's about a third. We said it was about 0.37 exactly. And now 1 minus 0.37 is 0.63. So what happens at t equals tau is that you're 63% of your eventual full value. So at t equals tau, you've gotten to 63% of your eventual full value that you can, with 37% left to go, of course. So we see, once again, this is a benchmark that we often use for exponentials, this thing called tau. So tau is, once again, the time to reach the 37% benchmark. So we took a look at this before. For instance, in this function right here, if you plug in t equals tau, you find that this is when you're at 37% of your initial value, right? So at t equals tau, you have lost 63%, and you only have 37% left. Of course, now that we're not dropping, but we're increasing the value, we're talking about increasing up to 63% with 37% left to go. Okay? So that may be something that you need to get used to in terms of these functions. This produces this because it's always the amount that you have at this moment. That's 37% of the original. And here we get this because we're growing, we get the 63% part of the 63, 37% cutoff, okay? So that's what the meaning is of tau in this circuit. Anytime something is growing, tau is the time to reach 63% of its initial value with 37% left to fill. It can again be determined this exact same way. You can figure out how long it takes to reach tau by looking at the resistor that you're trying to charge through and the capacitor that you're trying to charge. So if you are trying to charge through a larger obstruction, that's going to mean you take longer to hit your benchmark. And if you're charging a larger capacitor, it's also going to take longer to hit your benchmark. So that might look like this. You might have a second circuit with a longer tau value. If you're asking what's the answer for how long it takes to fill completely, the answer is always the infinity time. So instead we judge this by how long it takes to hit the 63, 37% benchmark. And if you're trying to charge through a larger resistor or into a larger capacitor, it'll take longer before you get there. I guess just as a little bit of an aside before I forget, for those of you that might not be comfortable with this as a mathematical entity, give you a little bit of a flavor for the type of questions that the homework asks. So the homework will never ask you how long does it take to fill completely, because the answer is always forever. So instead, it will ask you how long does it take to fill, say, some percentage. Maybe 99% is enough. So it might say, what is the time before the charge is 99% of full? Okay? That might be full enough for your purposes. So let me show you how you might solve this. Well, let's use our function. So this is how we do it. So first of all, if someone is giving you the amount of charge not just as a number, but as a percentage of the full eventual charge, that's a gift. Because this is what you do. You put in that you want to know at what time is this charge 99% or 0.99 of the full. So we put in the charge that we want, it's 99% of full, and then we solve for the time just by isolating it in the equation. Now, the nice thing about having it be expressed as a percentage of the full is that we just cancel off Q full. That makes it very much easier. So leverage that to your advantages. Again, if you solve symbolically, which I've been pushing since homework 4 on physics 1, you will find that things get a lot easier. So let's go ahead now. I'll show you how to isolate. If we have 0.99 equals 1 minus e to the minus t over tau. So we're looking to isolate t. If you understand how to basically do algebra and you're comfortable with exponentials, then this will just be a review. So first of all, I can't be isolating and doing anything with the exponential and getting the time down until I have the exponential by itself. So I'm going to group this term with this term. So I get 0.01 is e to the minus t over tau. Once you have the exponential by itself, you need to apply the inverse function, which is designed to get that t that you want down from the exponent. What is the inverse function to exponential? Natural log. So I take the natural log of both sides. So on this side, I just have minus t over tau, but I, of course, incur a natural log of 0.01, which your calculator is happy to do. And now, I just solve for time. T equals minus tau ln of 0.01. So you just throw in your tau R times C. Take the natural log of 0.01. And if you're worried about the negative and you're worried about traveling back in time, because we somehow got a negative time, I want to point out that natural log of 0.01 is negative. So you need an extra negative so the time comes out positive. Trust me, it comes out positive. So what you've solved for is the time it would take to get to 99% of full charge. Okay? And obviously that time isn't going to increase if tau itself is larger for this particular circuit, right? Because circuits with a larger tau take longer to do their thing. Okay, so that's just a little bit of an algebraic aside. That's your charging function. And of course, you can, once you have the charging function, you can always get the voltage function. So we did last time, we found that the voltage across the capacitor was this. It also has that 1 minus exponential business. Of course, it goes exactly as the charge does. Remember that Q equals C times V. So if that's what the charge does, that's what the voltage does. So if the charge grows exponentially, the voltage across the capacitor grows exponentially as well. We also found that the voltage across the resistor was this. So I did that for you last time. I didn't have a chance to do anything with it, but I believe I did get it last time. Just to remind you where that came from, that comes from Ohm's law. So remember, the voltage across the resistor tracks with the current. So if the current looks like this, so will the voltage. If I were to graph both of these, and they are both voltages, so I could graph them both together, it might be nice. So this is just a generic graph of voltage versus time. We see that as the charge grows in the capacitor, so does the voltage. So this is VC. It approaches the voltage across the battery. The voltage across the resistor looks like this. It starts off at the battery voltage and then decreases. So this is increasing while this is decreasing. These are things we already knew. We just now have the exact functions to tell us how that time progression proceeds. We already knew that the voltage across the capacitor increases from 0 up to the battery voltage. We already know that the resistor did the reverse. And now we just have the functions to describe them. Now, it was my claim that these two should always add up to the fixed value of the battery voltage, right? They both will add up to this fixed amount. If you don't believe me, you might say, look at these. These are both functions of time. If you add these two together, you will notice that all the time dependence drops out. And you do indeed get that the two are always going to add to the battery voltage. Okay? So really, they're just taking turns. The voltage across one is growing while the other one is shrinking. There's even a point right here where they meet. By the way, what is the voltage at that moment? Any ideas? So these are equal, right? Yeah, it's just half of the battery voltage. That's when they happen to have the same voltage. But remember, one's on the way up and one's on the way down. Is that T equals tau? No, because that's only the time it takes to go to 50%. Remember, tau is a 63, 37% benchmark, so tau would be somewhere a little bit this way, right? I guess I could call that T half or something, but it's not tau. So that's the basic gist of a standard charging circuit, you have these three things available. You just grab them. You just have to know what each of them is. Can't go wrong with the current function. There's only one current function. Then these are not really hard to mess up because they very clearly look mathematically, one is growing while one is shrinking. So you know right away which one's charging, which one's discharging. And then if you need to get anything else, that's enough. If you know the Q function, you can get VC. If you know the current function, you can get VR. You can get any of these potential energy or power functions if you want. They're all available to you. The thing that makes this particular circuit difficult is that you have to remember that the resistor and the capacitor aren't in lockstep. In fact, they're in series, meaning that when this increases, this decreases. So everything going on with the resistor goes to 0 eventually, and everything goes up with the capacitor grows from 0 up to its eventual value. Now there's one really handy kind of conceptual shortcut that makes this circuit easy to analyze, to visualize, and is also useful in other what I'll call non-standard circuits. So let me show you what that is. Are there any questions actually before I clear a little space? Okay, so one of the things that you can do when you have a capacitor that is empty, so it has no charge on either plate, and of course there is no voltage difference across the plates yet. It's completely empty. It's like a big empty parking lot. Plenty of parking. This, for all intents and purposes, functionally acts like a piece of straight wire, or as we call it, a short circuit. So short circuit, and this is an empty cap. So just like if we had a piece of straight wire, that would be an equipotential, right? There's no voltage difference on any point of this, right? There's no voltage difference across these. Now obviously they're not exactly the same thing, because if we have a particular charge that flows here, it just gathers up on this plate, and it's another charge that leaves the other plate. It's like a relay race. So if you were actually earmarking charges, it's not the same charge. Whereas if you have a piece of straight wire, of course it is. It's just one charge that goes straight through. So if you're getting down to the nitty-gritty level of the charge carriers, they're not exactly the same thing, but functionally they're the same thing. Let me show you. In our circuit, at first, when there was no charge across the capacitor, if we went ahead and we said that at the very initial state of this circuit, it was this, then we would have gotten the correct answers for everything. We would have gotten that the voltage drop across the resistor was the entire thing, which was what we said, and the initial current would then be calculated from that. So functionally, how an empty capacitor behaves in a circuit is basically as a piece of straight wire. Look at this diagram, right? This looks just like the voltage waterfall of something that has just one resistor in it, right? Now obviously that's not going to be true indefinitely. That's just true at the very beginning moment when the capacitor is empty. So what about later on? Let's jump all the way to when the capacitor is full. So we have a full capacitor. This is at the very end of the filling process. It's got plus Q full on one plate, minus Q full on the other, and it's gotten up to the full voltage drop across it, as set usually by the battery. Well, this is full up. It's a parking lot that has no more room, so no more charge would be flowing there. There would be no flow at all. Functionally, that acts exactly like an open circuit or a gap. just like no charge can flow across that because there's no way, there's no viable path through there. So a full capacitor acts functionally just like a gap in the circuit. So let's try that out. At the very end, essentially our circuit can be thought of like this. So of course, if we had a circuit like that with an opening or a gap, then the current would not be able to flow. There's no way through. Well, that's exactly what we find, right? There's no current at the end. This is an incredibly helpful thing to think about in a circuit when you're not sure what's going on. If you know the capacitor is empty, you can functionally replace it with a short circuit. And if you know the capacitor is full, you can effectively replace it with an open circuit. Okay? So it helps to